So you've been working with U substitution for a couple days now. This is our final day on this technique of doing antiderivatives with this U substitution strategy. And what we want to talk today is how to apply this to a definite integral. So first of all, we got to make sure we understand what a definite integral is. So let's look at the difference. An indefinite integral is one without bounds, where you integrate and you end up with capital F of x plus the constant c, which represents a family of antiderivatives that could all come from that same function. A definite integral, has bounds a and b, where you actually evaluate the integral on those bounds, and then you end up with capital F with the bound of b plugged in, and capital F with the bound of a plugged in, and the subtraction between the two. All right, so that's the difference between an indefinite and a definite integral. So when we apply U substitution to an integral that has bounds, we need to address the bounds as well. The bounds will not stay in their existing form. Okay, so what we want to do first is we want to identify what our U is going to be. So for this problem, we'll pick U to be the quantity 2x plus 1. And the du dx term would be 2 times the chain rule of 1. And so dx then by itself would work out to be du over 2. We also need to adjust our bounds. And so we take the lower bound and we run it through the U substitution. In other words, 0 is the lower bound when we were in x, when x was our variable. So I want to substitute that in for x and multiply. So 2 times 0 plus 1. So 0 is going to convert to a lower bound value of 1. 1/2 will also get run through our U bound. And so 2 times 1/2 plus 1. So 1/2 will be as converting to a value of 2. So my integral is going to look very different. My integral will have bounds from 1 to 2, 1 over the quantity u cubed times du over 2. So we can simplify that. We can pull the 1/2 out to the front. My bounds from 1 to 2, I can say u is to the negative third. And then I can find the actual antiderivative. So u to the negative 2 times negative 1/2 plus the constant c on the bounds of 1 to 2. Now, once we commit to using these new bounds, we never have to go back. We never have to go back to u in terms of x. We never have to go back to our bounds in terms of x. We can stay in these new values to get our final definite answer. So I've got negative 1/4 and then times 1 over u squared plus c going from 1 to 2. And like I said, I never have to go back to the original bounds of 0 and 1/2. I never even have to go back to the original value of 2x plus 1. That's one of the nice things about doing definite integrals, is that there isn't that resubstitution back at the end. You can simply just continue. So this would be negative 1/4 times 1 over 2 squared plus c minus negative 1/4 times 1 over 1 squared plus c. And so we're looking at negative 1/16 plus 1/4. So overall, we get 3/16 as our final answer. So one of the issues I'll see with students who do this is that they don't realize that they don't need to resubstitute, and so then they undo all of their work at the end and they put the x, the 2x plus 1 back in, and they change their bounds back, and they're just creating more work for themselves when they do it that way. So it looks like I duplicated a slide, so sorry about that. All right, so let's try another one. I can start with choosing my u, and I'm going to choose the denominator x squared minus 9. So how did I know that that was going to be the right choice? Well, when I rewrite this to the negative first, that's the one that's in the parentheses, so that's why I'm starting with that. I also recognize that the derivative is going to be linear. It's going to be 2x, and I already have the x piece as part of my product, so that's why I chose that. All right, and then we can move the differential of dx here, and so then dx by itself would be du over 2x. And now my bounds. So I'll take my lower bound of 0 and run it through my u substitution. So 0 is going to convert to negative 9. And then I'm going to take 2 and I'm going to run it through my bounds. So 2 squared. And so 2 is going to convert to negative 5. All right, so my new bounds are now negative 9 on the bottom, negative 5 on the top, x times u to the negative 1 times du over 2x. So the x's will reduce. The 2 will be 1/2 out in the front. My bounds are negative 9 to negative 5, and I'm left with the fraction 1 over u times du. So the format of that fraction is when I know that I'm going to be having an antiderivative that has a absolute value in it. So I've got 1/2 the natural log of an absolute value of u plus the constant c going from negative 9 to negative 5. So when I substitute in my negative 5 and my negative 9, that's where the absolute values become so important. So I'm going to end up with 1/2 of the natural log of the absolute value of negative 5 minus 1/2 of the natural log of the absolute value of negative 9. In other words, I'll factor out the 1/2. So I'll have ln of 5 when I apply the absolute value minus ln of 9. But if you remember your rules about subtracting natural logs, you could write your answer as 1/2 of the natural log of the fraction 5/9. That'd probably be one of the better ways to leave your answer. But you could also write this as the 1/2 being a square root. So the natural log of 5/9 to the power half. That's one of the properties of logs. And I could write that as the natural log of the square root of 5/9. And since 9 has a perfect square root, I could write that as the natural log of the radical of 5 over 3. There's lots of different ways you could write this as a final answer. Just know that, so if you're looking in the back of the book, or excuse me, looking in the answers and trying to match it up, that you could write it in any of those different forms. All right, let's try another one. Here's a product again. So we recognize that a product would be a good time to use a u substitution. We have two sets of parentheses, but one is clearly the derivative of the other, and so that'll help us make a choice here. And so I'm going to choose my u to be tangent of x. And then du dx would be the secant squared of x times the chain rule of 1. And then I can move my differentials. So I'll have my dx over here. So dx would be equal to du over the secant squared of x. And let's take a look at our bounds. So 0, and I'm going to run that through the x position. So 0 gets plugged in, and the tangent of 0 is still 0, so that lower bound did not change. My upper bound, I'll run that through. So pi fourths gets plugged into the tangent of pi fourths would be 1. So my new integral has a lower bound that stays the same and an upper bound that becomes 1. U is the substituting for tangent of x, and then secant squared of x does not get a substitution, but dx becomes du over the secant squared of x. So I've gotten a really nice reducing, and I'm left with about the easiest integral you can have, which is u du. So the antiderivative of that would be 1/2 of u squared plus c, and the bounds are 0 to 1. And I don't have to change my bounds back. I don't have to change my u back. I can substitute 1/2 times 1 squared plus c minus 1/2 times 0 squared plus c, and so we end up with 1/2 as our final answer. Right, so that's the last example. So just keep in mind that if things don't reduce, it means that your u choice maybe needs to be adjusted a little bit. And if you are doing a definite integral, that you never have to go back. It's only when you're doing an indefinite that you got to go back into its expression for x. But once you're in a definite integral, then you can stay committed to the new value of u and your new bounds. All right, I hope you have a good Wednesday, and I will look forward to seeing you either in person or online on Thursday. Have a good afternoon. Bye.